Hello, welcome to Joe's Classroom, and in this video I'm going to explain about the solvers for ordinary differential equations available in GNU OCTAVE. Though these soft solvers can be used to solve higher order differential equations, we consider only the first order differential equations in this video, and these same solvers can be used for both linear and nonlinear first order differential equations. Also, in this video, we will not explain anything about the numerical solution of differential equations. I mean the method of getting the numerical solution of a differential equations. If one is interested in those details, I would recommend you to watch another video on runge-kutta method, in which you will find all these details. When it comes to Octave, the solvers in Octave can be used to solve both explicit and implicit differential equations. Differential equations of the form y dash is equal to f of x comma y, where x is the independent variable and y is the set of solution variables. If you look at this form of differential equations, you are able to see that this y dash or the dy by dx or dy by dt, anyhow the first order differential term, can be separated in that equation, and therefore we are able to write the equation as y dash is equal to f of x comma y. And these type of equations we'll be calling as explicit differential equations, where the dy by dx term we are able to write explicitly. There is another class of differential equations in which this differential term y dash or dy by dx or dy by dt, anyhow the first order differential term, will not be able to separate from that equation, and those equations we can represent it as f of x comma y dash, that is equal to 0. So those equations are fully implicit differential equations. Octave has got solvers to solve both the explicit and implicit differential equations. When it comes to the explicit differential equations, Octave has got a unique solver associated with it, and in addition to that it has got some MATLAB compatible solvers also. The Octave specific solver is lsode, or in short you can call it as lsode. It uses an algorithm developed by the Lawrence Livermore National Laboratory of California, and this algorithm we call it as Livermore solver for ordinary differential equations. So that is why it is called LSODE, lsode. And this is a solver very unique to Octave, and even the Scilab will use this specific solver. And in addition to lsode, Octave uses some MATLAB compatible solvers also. When it comes to MATLAB compatible solvers, it has got two different class of solvers. The first class is a set of solvers to solve the non-stiff ODEs, and ode23 and ode45 fall into this class. ode23 is third order Boccacci-Champagne method, and ode45 is a Dorman-Prince method. So these methods are the variants of basically the runge-kutta method. And to solve the stiff ordinary differential equations, we have a linear multi-step method. It is ode55s. It is a variable step, variable order method based on backward difference formula. And as I said, it has got some solvers for solving the fully implicit differential equations also. So the solver what we use is ODE15i, and it uses the same method as this ODE15s with a slight modification. So this is a short overview of the solvers available in GNU OCTAVE. Let us see one by one. Anyhow, we will not deal with this fully implicit differential equations, and therefore ODE15i will not be explained. So we will explain how we can use lsode, ode23, ode45 and ode15s in an Octave script. So let us take lsode function first. Basically, lsode is a package which contains many numerical algorithms. It has got numerical integration algorithms, and it has got some predictor corrector algorithms also. The numerical integration methods available in this lsode function are implicit Adams-Moulton method of orders 1 to 12, and this particular method I can use it for non-stiff differential equations, and this is a variable step variable order method, and also it has got a backward differentiation formula method, BDF method. Usually it can be used for stiff problems. Of course, the methods which we use for stiff ordinary differential equations can be used for non-stiff ordinary differential equations also. Order of the methods vary from 1 to 12 in the case of AM method, and the order varies from 1 to 5 in the case of BDF method. However, when the algorithm starts, the first order method is used. As an integration proceeds further, the order of the method is adjusted by the algorithm itself for optimal efficiency. Not only the order of the method, but the step size is also varied for optimal performance. Let us see the syntax of the lsode function. If you look at this syntax given here, you'll be able to see that lsode function requires 3 arguments, and the result of the computation by the lsode function is stored in 3 different variables. So the arguments are fcn, y0 and x, and the variables on which these results are stored are y, I state and msg. Y is a matrix in which the solution is stored, and this is a mandatory variable to be used, and each row in the Y matrix will correspond to an element of the independent variable vector x. That means the values of the independent variable for which we need the solution will be there in the vector x, and the first element in this vector x corresponds to the initial value of x. And similarly, the first row of the Y matrix will correspond to the value of the solution variable corresponding to the initial value of x. That is what it means. That is, first row of the output is y0 corresponding to x0. The second variable is an optional one, and it stores the status of completion. If the entire computation by this lsode function is successful, then its value will be 2. And if the computation is not successful, then the value in this variable, the value stored in this variable will be something other than 2. So if you use this variable, you can find out whether the solution converged, and hence whether the solution is whether the computation is successful or not. And the message MSG is also an optional variable which will contain some additional information in the form of messages if the computation is not successful. So among the three variables y, istate and MSG, the mandatory variable is y. So that means you can use this lsode function even without using these two variables. When it comes to the arguments, the first argument is FCN. FCN is a string or inline or a function handle that names a function f of x comma y. F of x comma y is nothing but it is the right side of the differential equation when it is expressed in the form of y dash is equal to f of xy. So at every computation we need to compute this f of x comma y, and therefore we need a function to compute this f of x comma y. And here in this place of FCN, we will be giving the name of the function which is going to calculate this f of x comma y. So it will be in the form of a string. So usually it will be given within double quotes. And the second variable here is y naught. Y naught specifies the initial state of the solution variables. If it is a first order differential equation, y naught is going to be a scalar, and if I am going to use this lsode function to solve a higher order differential equation, y naught will be a vector containing all the initial values of the solution variables. Finally, x is a vector in which we will be specifying the values of the independent variable for which we need the solution. For example, if we need a solution for the values of x starting from x naught to x final, let us say, then this vector x will contain a series of values starting from x naught ending at x final. So this vector contains all the values of the independent variable for which we need the solution variable y. So this completes the syntax for this lsode function. So as I have already told you, lsode function needs a FCN, which means that a function handle to name the function which is going to calculate f of x comma y. Therefore, let us quickly review how a function can be defined in Octave. Syntax for defining a function is this. Function has to start with the keyword function and it has to end with end function. In the ending statement, this function is not mandatory. It can be ended simply with end. But still, it is always advisable to use end function instead of end, just to differentiate that this end statement corresponds to a function. Because in a script file, we will be using many end statements, even for loop or if loop or anything, or even for while loop. And therefore, just to distinguish that this particular end statement corresponds to a function, we can use the end function or simply end. Now, within this function and this end function, we have to describe what this body has to do, what this function has to do. The body contains all the statements and it says what the function should actually do. What is the, what the function has to compute or what the function has to do really. Apart from that, in the function statement, you will have two more things. One is the name for the function, it can be anything, and another variable in which you want to store all the computed values. So, whatever computation done in this body has to be stored in a particular variable, and that variable name has to be given here. And when I say this is the name of the function, it should contain a list of arguments also. This list of argument contains this list of arguments contain the variables which need to be passed this list of arguments contain the list of variables which are needed to be this list of arguments contain the variables this list of arguments or the variables which are to be transferred to this function during the computation of the program. For example, if this body or if the statements within this body of this function needs two variables, say x and y, then this argument list will be x comma y or y comma x. That depends on the usage of other statements or other functions which are going to use this function. So I'll repeat, if I need the variables x comma y to do computations inside the function, then the arguments, the list of arguments here will be x comma y or y comma x. So this completes how we have to define a function. So having understood the syntax for the lsode and the syntax for a octave function, let us move on to solve the differential equation. So the first order differential equation we have taken is this one. Dy by dx or y dash is equal to y into ln of y divided by x. So here it is the natural logarithm. Please note whether it is Octave or MATLAB. To compute the natural logarithm, the function used is log. If you need to compute the logarithm to the base 10, then the function is going to be log 10. But here, since it is a logarithm to the base e, we have to use the function log. And to solve any differential equation, you need the initial conditions, initial values for the independent variable as well as the solution variable. Here the independent variable is x and the solution variable is y. The initial value for the independent variable is 2 and the initial value for the solution variable is e. With this, we will see how we can create a script file to solve this differential equation. In my other videos on Octave programming, I have used the GNU Octave application downloaded and installed from the GNU website, but in this video I'm not going to use that. I'm going to use the cloud-based IDE of Octave, that is Octave-Online. You can very well search this in Google as Octave-Online. You will be able to see this Octave-Online Cloud IDE compatible with MATLAB. You can click it or you can even just type the web address octave-online.net, and this is what is going to be the screen. You'll be able to see the command prompt. You can very well use this command prompt, or if you want to use the script file, you have to log in. Just click that, sign in using Google. You will get the screen, and you can type in the Google credentials, and you can log in. So this is after logging in, the screen after logging in, and it has got different sections. The first section will display all the files saved in the Octave-Online, and the second section will have the tips and tricks, and it will display the script file also. You can create the script file by clicking that button, and if you click that button, the script file will be displayed here. And the third section will display all the variables that are used in the program after running it. And the fourth section is the console, and also you will see the command prompt there. Okay, so this is what is the Octave-Online screen. You can either start a new file, or you can upload the already created file which is in your laptop or desktop. So you'll create a new file. So just give an appropriate name. I will create a name as lsode demo, lsode-demo.m. So that file you are able to see there, and immediately you get the screen, the script file, the place for typing your script file. Let us start with the clearall command. The clearall command will help us to clear all the variables in the memory. And before that, it is always good to start with a comment saying the purpose of this program. And this program we are writing to solve the differential equation y dash is equal to y into natural logarithm of y divided by x. So that's the differential equation we want to solve. And the initial values for solving this differential equation are x naught is equal to 2 and y naught is equal to e. And also we need the solution of this differential equation from x naught is equal to 2 to x is equal to 10. Let us say from x is equal to 2 to x is equal to 10, we need the solution. So anyhow, already we have started the clearall command, and the one thing you should notice here is you can always toggle between wrapping and unwrapping the command. So we will clear the console also using the clc command, which will, this is the console, it will help us to clear the console before running the program. So the inputs to the program are the initial values x naught and y naught. X naught is equal to 2 and y naught is equal to e. And also you have to specify the final value. X final, we will take it as, and x final is equal to 10. Another variable or another input we need to specify here is the step size. We denote it by h. So we take the h value as 0.01. The smaller the h value, the higher the accuracy. And we need to write the command now for solving the differential equation using the lsode function. So we have already seen that out of the three variables, y is the mandatory variable and the other two variables are only optional. So we are going to use only this mandatory variable y. So if you are using a single variable, it is not necessary that you should use the square brackets. You can just put simply y, because you are going to use only one variable. So therefore y is equal to lsode, lsode, and the three arguments have to be given. So we will give the three arguments. The first argument is the function, then the initial values, and the last argument is the x values. Okay, let us type lsode of course you need to give three arguments. So the second argument is a direct argument, that is the initial value we have given is. So that is, this is the initial value. So y0 is given, and now we have to specify the function. It is always good to write the function code at the beginning of the program before start of the main program. And the function has to start with function and it has to end with end. And let us just write the body of the function, that is we need to calculate y dash is equal to y into natural logarithm of y by x. I have already told you that natural logarithm function is log divided by x. So that is what this function has to do. So we have defined the body of the function, and the whatever is calculated by the function has to be stored in the variable y dash, therefore that variable has to be mentioned here also. And we need to give a name to the function. We will call this function as simply as f, and we need to specify the arguments also. Arguments are nothing but the variables used by the function to compute something. So here y and x are the arguments. So please note that when we use this lsode function, we need to write the independent variable second and the solution variable first. Here the solution variable is y and the independent variable is x. So therefore it has to be mentioned as y comma x, not x comma y, because x is an independent variable that has to be specified as a second argument or as the last argument. So the function is over. So the function name is f, that let us specify here. The function is f. Since f is a string, we have to put it within quotes. And after the three arguments, two arguments are done with, and the last argument is x. You can notice that x is a vector specifying the independent variable values for which the solution is sought. So it is better to define the range of x. So here x starts from 2 to 10. So we will, let us define a variable x to store all the values of x for which we need the solution of this differential equation. So let us say x is equal to, so x starts from x naught and it goes up to x final, but with a step size of h. So 2, it will start from 2, then 2.01, 2.02, it will go up to 10. So we have defined the range of x also. So now let us give the range of x, that is x. So everything is complete. We have completed everything. Let us reduce unnecessary space so that we can see the entire code in a single screen. So now, having done with that, now what is pending is just plotting the variables x and y. So we will write a statement to plot the variables x and y. X is the independent variable and y is the solution variable. So we have completed writing the script file. Now it is time to save the file and also to run it. The Octave-Online says that there is inactivity, so it will expire in 5 minutes. So you can just press and enter so that it becomes active again. Yeah, it has become active. So now you can save the file again and run. Yes, you got the solution. You got the solutions. The output plot you got, the solution you got as a plot. So if you want to look at the graph specifically, you can click that. And if you click it again, it will go away. And the plot you can always download it as a PNG file or SVG file. So yeah, it is downloaded. Okay, so you can submit to your teacher or you can take it for your report or any thesis or something. So one more thing I would like to explain or mention here is the values of the independent variable can be given in another form also. You can use the linspace function. A linspace function creates a vector starting with x naught to x final, and here you're not going to specify the step size but the number of samples you need between x naught and x final. So this is another way to create the x vector. So in that case you don't need that previous two lines, they are commented. And again we will try saving it and running it. Yeah, you got the same output. So x vector can be generated in these two ways. Again, so we have seen about the lsode function, and we have seen how this lsode function can be brought into a script file. So we cleared everything, then we wrote the function to calculate the y dash. Okay, they specified the initial values, the final value, and we created a vector to save the x values, and for those x values we got the corresponding solution values, solution variable y, using this lsode function. So all these arguments are specified accordingly, and also we saw how we can use the linspace function also to generate the x vector or the variable independent variable vector. Yeah, you can notice here all the variables used in the program are listed here. So if you want to look at the value which is stored in that variable, you can simply click that variable and you can see what is the variable stored. So for example, x naught is 2. So any variable you can see by clicking it, or you can even type in the command prompt as we usually do in MATLAB. Now let us discuss about the MATLAB compatible solvers. The MATLAB compatible solvers are ODE45, ode23 and ode15s. So here we have taken the ode45 as an example to explain the syntax, and the same syntax can be used for ode23 and ode15s also. So when you compare this syntax with the syntax of lsode function, you should be able to notice three changes. One is in the variables on which the result of the computation are stored, and the location of the initial values, and also the way in which the range of the independent variables are stored. The first change is in the variables used to store the results of computation. In lsode, we used to have only the solution variable as an output. But here in the MATLAB compatible solvers, we have got two variables. One is x, which is nothing but the values of the independent variables for which the solution is computed, and y is a matrix in which the solution itself is stored. The FCN, as far as the arguments are concerned, the FCN is same as that of the lsode function, and the x range, actually in lsode function we defined it as a vector, and that vector, the variable containing that vector, was mentioned as a last argument. But here in this ODE45 or any MATLAB compatible solvers, the x range have to be mentioned as a second argument, and the second argument in the lsode function, that is the initial values y0, moves as a third argument. And there is one more change in the way in which this range of x is specified. In lsode, we need to have a vector in which all the values of x starting from x0 to x final have to be given. But here in this MATLAB compatible solvers, we need to give the initial value of x and the final value of x as a two-element vector. And as I said, the initial values are stored as the last argument. We have understood the syntax of ODE45, and now we will create a script file to make use of this ODE45 solver to solve the same differential equation which we solved using the lsode function. And rather than creating a new script file, we will use the same script file which we use for lsode, and here we are going to use this ODE45 syntax. So the first change is, as I said, instead of only y, we need to use both x comma y, and yeah, we will do that first. So you have to put x comma y, and the next change is, the range and the initial value, the location has to change. It has to go to the third place. Why not? The initial value has to go to the third place. And x range comes as a second argument. Okay, so what is x range? So you can see that x range specifies the interval of independent variables over which the ODE solution is required, and it is given as initial value and final value as a two-element vector. So we will specify we need the solution from x0 to x final. So x0 comma x final, and you need not specify this step because this ODE45 is an auto step algorithm. So the step size is decided by the program or the algorithm itself, and therefore you need not generate the x values also, which is also not required. So all the arguments are given. We will just replace this with ODE45. Another change what you have to make in the script file is the way you specify the arguments of the function. So in the lsode, we have to use the independent variable as a last argument, Okay, so but in for MATLAB compatible solvers, we have to use this independent variable as the first argument. Now let us save it. Yes, yeah, it's active. We'll save it. We will run. So we got the plot. Fine. So in the same way, we can download if you want. You can download as a PNG or SVG file, depending upon your requirement. And that makes. So in the same way, you can use it for ODE23 also, just replace it by ODE23. Okay. But if you use 15s, there will be a problem in Octave-Online. You'll be able to see this. Yeah, there is an error. It says that when this Octave-Online was built, this particular algorithm was not included in it. So ODE15s and ODE15i cannot be used with Octave-Online. So we will transfer this to the application which we have already installed in the system. So we will run it. We'll save the file as ODE solve. No errors. The solution we got. Yes, we got the solution. Okay, so for solving ODE23 and ODE45 and lsode, you can use the Octave-Online itself, or if you want to solve ODE15s or 15i, you can use the application downloaded from the GNU website. Here we complete, and thanks for watching.